Okay, so the recording has started. Now we can start today's session. Good afternoon, everyone. Welcome to this third interactive session for NPTEL course Solid State Physics. The course instructor is Professor Amal Kumar Das from IIT Kharagpur, and I am the teaching assistant Mrinalini. I am a PMRF research scholar from School of Physics, University of Hyderabad. If somebody is new, so these interaction sessions happen every Saturday, 3 p.m. to 5 p.m., where we sometimes review that week's lectures if some important concept is there or if you people have any kind of doubt. We discuss that, and then we also do some assignments related questions that will eventually help you in solving your assignment problems and in the exam if you're taking up one. Okay, so with this introduction, let's have a quick recap of the things that we studied and discussed earlier. So this is the list of recommended books that you find on the NPTEL website also. And then, yeah, so last session, in the second interactive session, we had discussed that for 3D, okay, just a minute. I need pen. We discussed how we have something called that we have lattice, right? Mathematical conceptual thing, and when we put group of atoms to those lattice position, we get our crystals, which is what making up, I mean, the whole 3D, any 3D material that we see. And then we were talking about that we have basically 7 type of crystal systems. That list we had seen, right? This is the 7 crystal systems that any matter that we see around us has this crystal system, which depending on the position of atoms has different Bravais lattice. So these 7 crystal systems give rise to 14 Bravais lattice, and their sides and angle relationship between their different sides and angles is like this. So this was, yeah, so this, after discussing this, we had seen that we considered cubic crystal, cubic unit cell, and then depending on if it's simple cubic, that all the atoms are at the corners of that cube, or if it's FCC with atoms at the faces as well, and BCC with the one atom at the body centered of the cubic crystal. So we derived the packing fraction. We derived packing fraction for these 3 crystal structures, and there were some other properties that we tried to understand how we can find out, like we number of lattice points per unit cell, volume of unit cell, how we can find, then packing fraction, and then coordination number also, which is also very important, that how many immediate neighbors atom has in a particular kind of cubic structure. Okay, so after discussing these things, just for quick recall, so the packing fraction for SCC was 52%, packing fraction for BCC was 68%, and packing fraction for FCC is the highest, which is 74%. Okay, this information is useful. And with this, okay, so there we had ended, and then of course we had done a lot of questions based on. So after understanding these packing fraction and crystals, we had understood that whenever we have not cubic but orthorhombic, or I mean crystal systems where the or any kind of crystal system where alpha, beta, gamma is the angle between these three axes, we had understood how we can define some direction, any direction, by taking origin, and we have to take care that this distance vectors should start from the origin. That will be convenient for us to find out the direction. And the direction we represent, let's say ABC, where ABC is the intercept on XYZ axis, and when we put it into this square bracket, which is just a bracket, then it represents direction. And when we have a plane, any kind of plane, then how to name that plane? We use something known as Miller indices, right? And Miller indices, again here also we first check what are the intercept of that plane on XYZ axis, then we take reciprocal of that number, and then whatever number we get, we try to make it into an integer. So we multiply it or divide it such a way that eventually we get, like for example, if the plane is cutting at 2 3 1, it's cutting x-axis at 2, y-axis at 3, and z-axis at 1, then so it will be like this actually. And then we just drop this ABC and we write 2 3 1. Then we take, for direction is just 2 3 1, but for plane, when we are naming the plane, then we have to take reciprocal. So this will be 1 by 2, 1 by 3, and this will be 1 by 1, that is 1. Then eventually we have to put it, make it integer. So here if I multiply with 6, then this will be 3, this will be 2, this will be 6. Yeah. So this is how we'll get integer, and then I'll put it in this. This is called parenthesis or curly. Or just bracket, circular bracket. Usually it's called parenthesis, if I'm right. Yeah. And then this also should be understood that maybe we can discuss it again if we have time, or otherwise that when we have family of directions, like if this direction, if what I want to say is, like for example, this red direction is say 110, okay, because it's cutting here say at 1, cutting here at 1, and not cutting in 0, so 110. Now if I take another only to this distance, so it will be like half here, right? So just think, maybe it's 220. So their direction is same. These magnitudes will be same, but they are representing the same direction. So in that way, these are pointing to the same direction. Then we can write it like this, that the family of direction representing all, this represents all 110, 220, 330, kind of all everything. So this kind of greater than, smaller than symbol we use to represent family of directions. Okay. Now similarly, when we have family of plane, like, let me draw again. This is x-axis, this is y-axis, this is z-axis, and say, okay, let me draw this. If this is my one, it's intercepting at 1 1 1, then I'll call it 1 1 1 plane. Now if there is a plane that is cutting here at half, and here at half, okay, now these two will be parallel, only it's cutting at half the distance, but these two planes will be parallel. So for the smaller, this another one, it will be 2, 2, 2, the Miller index. So these are parallel. In fact, there will be a 3, 3, 3, 4, 4, 4, which will be even smaller and smaller. So all these are parallel to each other. Maybe the atoms are all same. In that case, if they are identically same, sometime maybe the atoms on 1, 1, 1 plane is not same to 2, 2, 2 plane, then we cannot call them same. But if they are same, then we can represent it like this curly bracket, or that we call braces. Okay, and when I represent it like this, it means all 2, 2, 2, 3, 3, 3, all those. Automatically, whenever you see written it like this, that means that it resembles all 1, 1, 1, 2, 2, 2, 3, 3, 3 on all those planes. So then we use this curly bracket or braces. So this is how we represent these different directions, family of directions, planes, and family of planes. Okay, so these were the things that we had discussed. Now we'll move on further, and the things that was covered in this week's lecture, there was kind of little derivations for like interplanar distance and other things. So because it was in very good detail, so I don't think we need to repeat it. So I'll just write the final formula and we'll focus on other concepts. Okay. So yeah, these were the crystal system Bravais lattices that we discussed. Okay, so the first thing covered was interplanar distance, how to find out interplanar distance when we have parallel planes. Okay, in this case, if you remember the diagram, like if we have x-axis, y-axis, z-axis, and yeah, again let me take okay. This is origin O, and let's say it's intercepting at A, B, C, and the intercept here is, how do we know like how much is the intercept? Because if I'm calling this plane is my HKL plane, okay, if I'm calling this is my HKL plane, and we know how we get to the Miller index. First we see the intercept at XYZ axis, then we take reciprocal of those numbers, then we get this. That means the intercept will be reciprocal of this. And also we have to multiply it with A. Just to make it clear, what I mean is, if this is my Miller index, then my intercept on x-axis will be A by H, intercept on y-axis will be B by K, and intercept on z-axis will be this. Why? Just to recall how I ended up, how I am sure this is correct, because when we check that this is the intercept, then first thing we do to make it to Miller indexes, we drop this ABC and just take the magnitude, right? And after that, the next step is take the reciprocal. So here if I'll take reciprocal, I'll get H, here it will be K, here it will be L. And then if it's still not an integer, then we try to make it into an integer by multiplying or dividing it. So here there is no need. So this will give me my HKL Miller index for the plane. So this is the way to get the Miller index for plane, and the reverse of it will give me the intercepts on XYZ axis. So if HKL, this plane is HKL plane, then the intercepts will be these. I hope you understood. So these are the intercepts. So based on this, the interplanar distance, or the distance from this origin to the plane, if you want to find out the distance from this side, if I just show you, so it's like y-axis is here and my plane is cutting this side like this. Now I'm drawing a perpendicular to this plane to find out what is the distance from origin to this plane. And the formula becomes, let's call this distance, the normal distance, d, and we are just putting this subscript HKL to represent that we are talking about the interplanar distance between this HKL plane. Okay, so the formula for distance, which you can see from the video, I just didn't want to repeat the derivation again, so we'll just get to the formula. So this will be h by a square plus k by b square plus L by C square. This will be root to the power minus 1 by 2, means this whole expression is in denominator and also under square root. This is the formula, and just to see, if I keep what is the interplanar distance between 1, 0, 0 planes, then it will be, we have to substitute h is equal to 1, so this will be 1 over a whole square, and other things will be 0 to the power minus half. That means 1 over a square to the power minus half. That means a square, square root of a square means a, and we have to take reciprocal, means a. So the distance between 1, 0, 0 planes will be a, which we know. If it's a cubic lattice and we are talking about this is 1, 0, 0 plane, the back one is also, then what will be the distance between them? It will be a, that we got from this formula. Here it's easily to visualize also, but sometime if it's something complicated, like if my HKL is 132, then it may not be easy to draw and then check. So this formula is there to help us out. Okay, so the next thing was angle between two crystal planes. Now here we had parallel planes, and then we were trying to find out the distance between them. And now, so this was, interplanar distance, the distance between two planes. And then, so to tell you angle, how we find out angle between two crystal planes. So as was in the lecture, if we have these two planes, then after doing some derivation, we can find out this relation. In case if you guys didn't understand the beginning where the professor was talking about that direction cosines, so I just want to explain you this, because we were talking about this was our DHKL normal to the plane DHKL, and then to understand how we take direction cosine of this D vector corresponding to x, y, z axis, I just want to show direction cosines means whatever that vector is, what is its cos of that angle that it makes with x-axis, y-axis and z-axis. This is our direction cosines. Like here you can see this black vector, black color vector. You see this? Its angle with x-axis is some theta x, or here it's represented by a. Then its angle with b axis or ey here is this. Its angle with z axis is this. So those three angles and their cos, which is a trigonometric function, cosine, is what gives us direction cosines. Because it was not given in detail in the lecture, so I thought just to clarify, I'm giving you these values. And in case if there was also some confusion, just to clarify, in the beginning, like the professor had directly written that DHKL is equal to A by H cos phi A. So if there is any doubt in that also, so I want to explain you that if this is my say this is my x-axis, this is any other axis, and this is my main vector, and this it's making some angle, say phi. Okay, then I have to find out this relation, right? Now this was my DHKL vector on the plane. I'm just giving you side view, so I'm not drawing the plane. This was the perpendicular to the plane from the origin. Now when I take intercept of this vector on x-axis, this will give me some length. Let's call it x. Then you can see x here will be DHKL cos phi. So for like if I have, let me take another slide. Yeah. So if I have coordinate axes arranged like this, and this is my DHKL, it's perpendicular on the plane. Okay, this is DHKL, and this vector is making angle, just use some other color. So if its angle with x-axis is, let's call it phi A, angle with b-axis, let's call it phi B, and its angle with z-axis is phi C. This is my x-axis, this is my y-axis, this is my z-axis. Okay, now in this case, you see DHKL, if you put a perpendicular, right, if you drop a perpendicular here, then you can see by trigonometry in this right angle triangle that, and this intercept will be, this will be b by k, this will be a by h, this will be k by l, sorry, c by l. So basically what we see, b by k is equal to, or we can write DHKL is equal to, we know, right, it's base by hypotenuse. So cos of phi A, cos of phi A will be, or here this is better to see, so we'll take cos of phi B will be base upon hypotenuse, A by h. Okay, and similarly we had got that DHKL was equal to A by h, cos phi A equal to B by K cos phi B, because then right now I have made like this, and next you can make it x here and DHKL, because in 3D we are not able to see it like this, but if you'll just move it, turn it by 90 degree, then x-axis will be lying here, and you will see the intercept of DHKL or drop its intercept like this, right? Then you can do the same relation for that. So that is what, and we will get C by L cos phi C. So using these direction cosines and the rule that cos square phi A plus cos square phi B plus cos square phi C will be equal to 1. This formula was derived, right? It gives cos theta relation and the angle between these two planes. So finally the formula, the angle you will get by taking cos inverse of this whatever number you will get, then you will get the angle. um, so yeah, it's written very well. And family of planes we understood, family of directions also we understood. I think so. Based on these things, first let's discuss some problems. After that, if we have time, we'll start next topic. Okay. So the first question is find out the linear density of FCC crystal. So here we have to talk about. Let me change. Red is better. Find out the linear density of FCC crystal in the direction 100 in terms of atomic radius r. So first, let's draw, or yeah, just this is better. Its FCC means there will be atoms on the corners. In a cubic arrangement means we have 8 corners, so 8 atoms at the corner, and then we have atoms at all the faces. We have 6 faces, so 6 atoms. Okay. And then here what it is asked is linear density. A volume density, mass density, we understand mass density is mass per unit volume. Or in packing fraction we were seeing how many atoms are there in a unit crystal. Here by linear density of FCC crystal in this direction, what we mean is how many atoms are there in this along this direction vector. Now if I consider this is my origin, this is x-axis, this is y-axis, and this is z-axis, then you'll see if I make, or let's make x-axis here itself, this is y-axis, this is z-axis, that means this corner is our origin. Now we have to take 100. Now we know 100 direction is this, because this plane, the front one, is intercepting x-axis at 1. So this is 100 plane because it's not intersecting y and z-axis. And perpendicular to this plane will be 100 direction. Right? So this direction is our 100 direction. Now along this direction, how many atoms are there? Okay, linear density means how many atoms are there on this distance. So this distance, if I draw, this is my origin and this is say A or capital A, and this distance, let's call it small a. So this is my origin, this is A point on x-axis, right? And here you see there is one atom. It will be like this, right? Because it's being shared by other atoms also. And just to show you that this face, this particular face, right? On this face, this line is there, and there is another atom like this. Okay? So here, although on this line there are two atoms, but the line is not completely owning these two atoms. What I mean is, one atom is like this, and our line or direction vector 100 starting from its center and going to the center of the next atom. Here, if the diagram if I show you better, so it's like one atom is here, one atom is another corner, right? One atom is another corner. So even this extension we are showing because it's the x-axis, which is imaginary, right? X, Y, Z axis we always use, but they are not in 3D space actually some lines like this. It's for our understanding. But this direction vector we are talking, it starts from here, it ends because the atom is here. So this direction, we have only two atoms as far as FCC crystal here is concerned. So it starts from the center of one atom and ends at the center of another atom. That means how many atoms do we have on this line? The length of this line is A, of course, is the side of this FCC cube. But how many atoms are here? There is there are two atoms here, but their contribution is only half. Because if it will be lying completely, if this line will be crossing it completely, then it will be contributing completely to the line. Here it's only starting from the center, so it's only taking half of it. Okay, so every sphere or every atom has half contribution atoms. That means total one atom we have here. Okay, so number of atom I hope is clear. If you have doubt you can ask. So number of atom on this direction vector total will be 1, and the formula for linear density will be number of atoms and the length of direction vector. Length of the direction vector here, the length of 100 direction vector. Okay, number of atoms I told is 1. Now the length. Now length is A, but we have to give the answer in terms of atomic radius. Okay, so for this purpose, you know, in FCC, the linear density of this, right? So for FCC, what is the relation between FCC? Yeah, so the relation between in FCC, if you remember, we had done this when we were trying to find out the packing fraction. That if we take one plane of FCC, then I had told you, although I just draw it very small so that we can clearly see all the atoms, but in reality, for FCC, as far as FCC is concerned, we have atom at the center, and this is also not. Actually, it is like this. This we had understood when we were trying to do the packing fraction, that one atom is like this at the corner because it's being shared by 7 others, and then there is one at the center touching each other. So at the face diagonal, these 3 atoms are touching each other. Then there is another one here, another one here. Okay? These 3 are also touching each other. And the side of the cube is A, and this is R, this is R, this is R, this is R. So what we saw here, this is A and this is A, means the face diagonal will be, because this is a right angle triangle. If you see, we had done all these things. If you still have doubt, you can watch last time's interactive session. There we had discussed how to get these from Pythagoras theorem. That's it. If once this is cubic, this is so if this face is A, this face is A, that means this diagonal will be root A. And this root A, because all the atoms are touching each other along this length, so we can equate root A is equal to 1, 2, 3, 4. 4R. So here we have 1 by A, and A answer we have to give in terms of R. So A and R, the relation is this. That means A will be 4R by root 2. 4R by root 2, if we further simplify, it will be 2 root 2 R. If I'll substitute that here, I'll get 2 root 2 R. So the correct answer will be answer C. 1 over 2 root 2 R is the linear density of FCC crystal along 100 direction. Okay, I hope this is clear. Still, if there is any question, please ask, or anyway, we are going to do many similar questions now. So I hope it will be clear. Okay, so the next question is, find the linear density. Again, it's a question where we have to find out linear density for FCC crystal in the 111 direction in terms of atomic radius r. Okay, so here what we have to, earlier we found it in the direction of 100. Now we have to find it in the direction of 111. So again, what is 111 direction? So if I draw this, my FCC crystal, okay, this is my x-axis, y-axis, z-axis, and FCC means all corners. Atoms are situated at all 8 corners, and then all the faces, but I'm not drawing all the faces, otherwise it will get confusing. First let's see which direction we want, this 111 direction. If you, I think by now you have understood what is our 111 direction. So when we have a plane like this which is making intercept at 111 at all 3 axes, that plane is 111, and then direction perpendicular to that, it's like out here, that will be 111 direction. So in this cube, if you will see that 111 direction will be this body diagonal. If this is my origin, then from this 0 0 0 coordinate to this 111 coordinate, if I draw a line, this point here to the point at this front, this is body diagonal of this cube, and this is also our 111 direction. Okay, so first step is to identify the direction in the cubic crystal, and next we have to see how many atoms are there on this. Now again, this is similar situation as previous, that we have how many atoms here again, because it's FCC, so all the atoms are on the faces, right? I'm not drawing, or if you want I can draw. They are all on the faces, but this 111 line, this face and then this face, top face, bottom face, then front, this front will have 1, then back will have 1. Don't get confused, this one is at the top face, this one is at the back face. Okay, so these 6 atoms are on the faces, but on this direction vector there is they won't lie. So on this 111 again we have the same situation, only 2 atoms. That means the number of atoms for our linear density here, its contribution half, so total 1. So we have 1 atom on this direction vector. And what is the length now? So again, if you recall, we had seen that the phase diagonal, I told you, phase diagonal is root 2 times A, which is the side length, because all are cubic, so that means everything is A. Phase diagonal is root 2A, whereas body diagonal is root 3A. And this derivation also I had shown you last time. So if you have doubt, please go back to that lecture and see. This is root 3A. Okay, body diagonal. So here we are talking about this length, which is body diagonal. So I'll write root 3A. Now we have to give the answer in terms of atomic radius. The same thing for FCC, we saw just here that for FCC root 2A is equal to 4R is the relation. What was it? Root 2A is equal to 4R. Okay. And how we find out? We check these 3 atoms touch each other along this phase diagonal. From there we get the relation between A and R. That means A is equal to 2 root 2 r. So if I substitute value of this here, I'll get 1 over root 3. A is 2 root 2 r. After multiplying, I'll get 1 over 2. Root 3 times root 2 will be root 6 r. 1 over 2 root 6 r is the linear density here. So the correct option is option A. Next question. Yeah. Calculate the values of linear density again along 111 direction vector for FCC, which is copper atom, and here we have been given that atomic radius of copper is 0.128 nanometer. Okay, so till now we were finding out the values in terms of r variable, which was the radius. Now we have been given the value of that radius also, so that we can finally tell what is the actual with magnitude for linear density. So the procedure is same. We have to identify which direction it's talking about, and just now we did 111 direction for FCC. We have done already, and yeah, so linear density relation we just did. The whole procedure is same. We have to first make this FCC cubic crystal, identify the direction, which is the body diagonal, and then see how many atoms are lying on this direction vector. We can see half of this, that means effectively only one atom on this line or this direction vector, and then number of atom divided by length of that direction vector. Since it's a body diagonal, it's root 3 times A. Now A in terms of radius will be 2 root 2 r. So final answer is 1 over 2 root 6 r. So linear density here will be 1 over 2 root 6 r, right? Yes. Now r is given here, which is 0.128 nanometer. When we'll put the value of r here, 2 root 6 times 0.128. Now the answers are in per meter, and here it's nanometer. If you don't know, let me tell you, 1 nanometer is 10 to the power minus 9 meter. Nanometer is 9 orders, 9 times smaller than a meter. This is the relation, and if I change it into meter, I will make it 10 to the power minus 9 meter. Okay. And when we will do this calculation, let us do this. So 2 times root 6 times 0.128 0.6271 10 to the power minus 9 meter. This all is in denominator. When I'll do this division, I'll get 1 divided by 0.6271. This will be 1.5946 times 10 to the, this will go in the numerator, so it will become plus 9, and this meter will become meter inverse. So the correct answer is, the closest here, its matching is this. Okay, so the linear density for this particular problem, the correct answer is answer C. Okay. Next question, find out the linear density for BCC crystal. Okay, now pay attention, it's BCC crystal. We know it has atoms at all 8 corners and then in the center of the cube, that is at the body. And now we need to find out the linear density for a BCC crystal along 110 direction. Let's first make our, I think the best thing is first to quickly draw a unit cell diagram because it helps in visualization. Okay, so this is our cubic crystal, let's say this is x direction, this is y direction, this z direction, this is origin. Now BCC crystal means atoms, all the corner. Oh, we have atoms at all the corners. Okay, and then one at the center. I'm not drawing, again it will be confusing, but there is one at the center. Okay, now next is to identify the direction. 110. 110 will be this direction. How? Oh, yeah, don't know why it's okay. This is our 110 direction. Oh, because 110 plane will be intersecting. If you take intercept of this direction vector, on x-axis it's intercepting at 1a, on y-axis it intercepting at 1b, and it's not intersecting z-axis. So this will be our 110 direction. Or you can understand that 111 plane will be this, right? Let me use another color, or I'll draw separately here, that if whenever we have a cube, you know, right, this is 110 plane, and perpendicular to it will be, because it's cutting x-axis on 1, y-axis at 1, and it's not cutting z-axis, so this will be 110 plane, and perpendicular to it the direction vector will be 110. I hope I could make it clear. Okay, so this is the direction vector of interest here, 110. Okay, now we have to find out how many atoms are there on this line, because it's body centered cubic crystal we are talking about, and this 110 is on one particular face here. This is on xy plane, and the body centered atom will not touch this because it is at the center of the cube. That is, it's not on the face, it's in the center of the cube. So on this line only this will be there. So again the contribution by this will be half, and the contribution by this will be half. So number of atom total will be 1, right? So linear density for this particular situation, number of atoms 1. And what is the length? Because again you can see if the side is A and it's a cube, so all sides are equal, that is A. Then this is phase diagonal again, and phase diagonal we know the length of phase diagonal is root 2 times A. So root 2 times A. Now we have to answer in terms of radius. Now for BCC, what is the relation between the edge length A and the radius of the atoms? We had seen till now for FCC, but BCC we know it's different. Okay. Let's take one more slide. We'll take one slide, and although yeah we have done it already, you can see from there, but just for quick recap. So in case of BCC, what happens? In the center we have one like this. Again this thing is, I have to make it big enough. Yeah, and they are touching. Ignore this smaller one. So we have 3 touching, but where are these? Now these are not on phase diagonal like FCC. The one at this corner, the one at this corner, and one at the body center. I'm talking about the body diagonal here. For finding out this relation, we have to consider where these 3 atoms are touching each other so that we can get the correct relation between R and A. So this is A, okay. I mean, this is body diagonal, means it will be root 3A. One direction will be root 2A, face diagonal. This again you go and see in the previous video. We had done the derivation in detail. So just understand, one is A, one is root 2A. This is face diagonal, and then we have this from A to B. This length is root 3A. This is the length of body diagonal, which is equal to this R, this R, this R, and this R, right? 4R. Now, okay, actually I should use capital R because in answer we have capital R. So the relation here, A is 4R by root 3. So this is the relation. So linear density was 1 over root 2A. So linear density was 1 over root 2 times A. When I substitute the value of A here, I'll get 1 over root 2 4R by root 3. This will become 1 over root 2 root 3 divided by 4R. So our answer will be root 3 by 4 root 2R. Root 3 by 4 root 2R. So answer A is the correct option. Okay. Next question. Calculate the linear density. So it's a question of linear density. We have a lot of sufficient questions. I hope doing all this will make this concept of linear density very, very clear for you people. Okay. So calculate the linear density for BCC crystal. We have to find out linear density, and this time we have BCC, and we have to choose 1, 1, 1 direction, and the answer will be in terms of atomic radius. And the edge length or the is A. Okay. So again the same thing, or let me first draw it like this. This is the x-axis, this is the y-axis, this is the z-axis. Okay. Now again, this is origin, and we have atoms on all. Again this started. Actually I'm using the writing pad and my hand starts taking, instead of pen, my fingers which is touching it. So these are atoms at the corners, and then one at the center of the cube, which I am not drawing here for time being. Now so we understood this is our cubic crystal, and next is direction, 1, 1, 1 direction. Now we know 1, 1, 1 direction is which direction? This is very bad diagram, but this is 1, 1, 1 plane, and perpendicular to it is our 1, 1, 1 direction. If this is x, y, and z axis. I'm very sorry, this is very bad diagram, but what I want to say is the 1, 1, 1 direction will be the one joining this at the back and this corner in the front. This will be 1, 1, 1 direction vector. Okay. Now this is some fun now, because this 1, 1, 1 direction, remember we have a body center atom here lying on this 1, 1, 1 line, because this 1, 1, 1 line, if you see, it's a body diagonal because it's connecting the corner at the back to the corner at the front. So this is a body diagonal, and we know because it's a BCC crystal, we have one atom completely lying on this line. So now, how many atoms we have on this line, on this 1, 1, 1 direction? One like this at the corner, one like this at this corner, and one in the center. Now please remember these three on the body diagonal, they touch each other, but again because I could not draw it like this, so sorry, but they are all touching each other, okay? And these are three atoms on this line, 1, 1, 1. So to find out linear density, what is our formula? That in numerator we have number of atoms. So here total how many number of atoms are there? The corner atoms are contributing half half. We have two corner atoms and their contribution is only half. And then we have one more atom which is completely lying on this line, right? That means this from corner atoms and then one hole in the middle. So in total we have two atoms on this line 1, 1, 1. Then what is the length of that line? Since it's a body diagonal, we know body diagonal's length is root 3a. Root 3a is the length of the body diagonal. Now the answer has to be given in terms of radius. Now we know for BCC, the relation we just now saw, relation between the radius and the edge length is root 3 is equal to 4r. So root 3a is equal to 4r. That means a is 4r by root 3. When I substitute it here, I'll get 2 divided by root 3 and the value of a is 4r by root 3. Root 3 will cancel. I'm left with 2 by 4r, which is equal to 1 over 2r. So the answer is 1 over 2r is the linear density here. Okay. Next question. Calculate the value of linear density along 1, 1, 1 direction vector for BCC, which is iron. Okay, so just now we did the same thing. So we'll use this linear density relation directly from here because this was also for 1, 1, 1 and which was a BCC crystal. So the linear density for this is 1 over 2r. So here also linear density will be 1 over 2r because we have to find out for BCC crystal and the direction is 1, 1, 1 same. Okay, now we have the value of this radius, which is 0.124 nanometer, and the answers again are in meters, so we'll change this into meters. I told you 1 nanometer means 10 to the power minus 9 meters, so this will be 0.124 times 10 to the power minus 9 meters. Okay, now when we substitute it here, it will be 1 over 2 multiplied by 0.124 times 10 to the power minus 9 meter. All this is in the denominator. Let's do some maths here. I have my calculator to do this. 2 times 0.124, 0.248. So 1 over 0.248 times 10 to the power minus 9 meter. Then we take reciprocal, 1 divided by 0.248 will be 4.0323, and this will be this will go to numerator, it will be 10 to the power 9 and this will be meter inverse. So answer that matches here, all the answers are up to 2 decimal digits. So here when we'll round off, it will be 4.03 10 to the power 9 meter inverse. So correct answer is B. This is the linear density for this question. Okay, now next, okay, this is something different because here we have to find out the planar density. So the question is, calculate the planar density of FCC crystal for 111 planes in terms of atomic radius r. Consider lattice parameter of cubic crystal is A. So till now we were finding out the linear density, that how many atoms are there on that particular direction vector. Now we have to see how many atoms are there on that particular plane, which is 111 here. FCC. Okay, first let's draw our FCC cube. First thing we should do to make things clear. This is our x-axis, this is our y-axis, this is z-axis, this is origin. FCC means we have atoms. Let me use this time some other color to make. We have atoms, corners. And then again, just to keep it clear, I'm not making, but we have on all 6 faces we have 6 atoms. Now drawing is done. We need to find out which plane we are talking about. 111 plane. Which is this 111 plane? I can draw here again, but just to keep it separate. 111 plane is the plane that intersects. Again, let me use another color. So 111 plane. I'm sorry for this shabby diagram because I'm not using pen and paper. I'm using this writing pad. That's why I'm not right now able to control it very well. But I hope the things are clear. That this is a straight line. Okay. So 111 plane will be this. Okay, it's intercepting x-axis at A, y-axis at B, 1B, 1A and 1C. So this red thing is our 111 plane, and this is how it looks. So here if I'll draw, it will be like this. So we understood this is the plane. We need to find out, and we want to find out how many atoms are there on this. Now here we understood this is our plane, and also we have atoms on all the corners for this FCC. So that means we have one here, we have here, we have here also, but that is not lying on this plane. So we have here also, but that is also not lying on the plane. We have one at this corner also, but please be careful, this plane is not touching this corner, right? This plane does not touch the corner. It's in between these edges. So the one at the top won't lie on the plane. The one in this corner, these 3 atoms only will lie on this plane. Okay. So only these 3 will lie on this plane. So that means how many are there? Okay. No, just to be careful. Okay, this I have drawn the corner 1, 2, 3, 4. Yeah, one at here, here. So 8 atoms are there. Out of these corner atoms, so 8 corner atoms we have. Among these 8 corner atoms, on this 111 plane, only these 3 corner atoms are there. Only 3 corner atoms lie on this plane. Okay. But what about the face-centered atoms? Let's use some other color. We have one atom on this face, right? On left face. Then one atom on right face. One atom at the bottom. And then of course one on this face, one on the top face. So we have 6 atoms on these 6 faces, but out of those 6, again we have 6 faces, so 6 atoms. But out of those 6 atoms on the 6 faces, how many atoms are on this plane? So see, this plane, this 111 plane is touching this plane, this left plane, and there is an atom there. Then it's touching this back plane. Sorry, this is a straight line. Oh no, what happened? Okay. Shit. Sorry. I don't know how everything got erased. Anyways. Share. Anyways. Okay. Now this is one edge of this one plane, and this one atom on the face is lying on this plane. Then it will pass through this down face also, where also there is one atom which will also lie on this one plane, and then at the back face, this back face, right, there is one atom on the face that will also lie. So we have 6 face atoms, but out of those 6 only 3 will lie on this plane. So how will it look eventually? It will be something like this. 1, 2, they're all touching. Then this, then this, then this. So our 1 plane, I'll tell you how is it. So this is like this one. Let's call it A. This is A atom. This is B atom. This is C atom. Okay. This 111 plane is covering A atom, B atom, C atom, which are all the corners. Okay. And then on this face, this is let's say P. This is P atom. This is Q atom, and this down one is R atom. So this is that P atom, Q atom, and R atom. I hope you are able to correlate these two diagrams. That on this 111 plane we have 3 corner atoms A, B, C, and we have 3 face atoms P, Q, R. So on this plane, 111 plane, we have these many atoms lying, but now we need to see that how many are total effective contribution is how much, because for linear density we used to see if the atoms are like this, then its contribution is only half. So here also we have to see what is the total contribution. Okay, so here if you see the face atoms, here we are not talking about linear density, be careful, we are talking about plane. So these atoms are only lying half, because on this plane their contribution is only half, right? Explain. Because only the atom which is inside of this cube is lying on this plane, the outside one will be part of the other cube, right? This atom on the face, right side of it will be in this cube, the left side will be in another cube. So only we have to consider which is inside. So that means it's only contributing half. The same way this is only contributing half, which is inside in the cube and lying on this plane. So P, Q, R, the face atoms P, Q, R will contribute half. What about the corner atoms? How much they are contributing? We can see it's very less than half. So how to know that? So what I'm saying is we have 3 at the corners, right? And 3 on the face, and this is 111 plane. The edge length, what is the edge length? Oh, the edge length is, this edge of the plane is phase diagonal actually. This is a phase diagonal, this is also phase diagonal, this is also phase diagonal. That means this edge is root 2a, root 2a, root 2a. All sides are equal. And all angles are also equal, because the angle here between this edge length, all angles are equal. If all sides are equal, all angles are equal, that means this is an equilateral triangle. This 111 plane is intersecting and making equilateral triangle here, right? And these atoms we are calling A, B, C. Okay, this is A, this is B. We can do little short also, but so that you are able to understand this whole planar density thing properly, I'm trying to clear these small things as well, that how we know how much the corner atom is contributing to this plane. So to understand that, we have to, I can just straight away tell you that this is equilateral triangle, but just to make it clear how we understand that, we know this 111 plane is touching the faces like this, all the sides are equal, all angles are equal, that means this is equilateral triangle. And since we know for a triangle, sum of all the three angles for a triangle, sum of all three angle is 180 degree. This is property of a triangle. It can be any type of triangle. It doesn't have to be equilateral. It can be isosceles, scalene, right angle triangle, any kind of triangle. But if it's a triangle, then sum of all three angles will be 180 degree. Now we know it's an equilateral triangle. That means all angles are equal. Let's call this is theta. And sum of all angles are 180 degree. Means theta plus theta plus theta is 180 degree. That means 3 theta is 180 degree. That means value of one angle is 60 degree. One angle is 60 degree. This angle is 60 degree. Okay. Now this whole thing remaining will be how much? Because the total is, of course, a circle is 360 degree, and we are taking 60 degree. That is only this part of it. That means how much we are considering. This is 1/6 part only of this whole atom. That means why we did all this exercise, to understand. If you can visualize, then also very good. If you can just visualize that this contribution is 1, 2, 3, 4, 5, 6. It's 1/6 part only. Good. Otherwise, you can do this little maths to understand that when we are considering this plane, then the corner atoms are only contributing 1/6 to this plane. The remaining is in another planes. So we understood that the face atoms are contributing half and corner atoms are contributing 1/6. That means total number of atoms on this 111 plane is, so contribution from corner atoms is half, from the face atoms is half, and we have how many face atoms? We have this P, Q, R, 3 face atoms. Okay, plus contribution from corner atom is 1/6, and we have how many corner atoms? Atom A, B, C. So we have 3 atoms on corner as well for this 111 plane. So total number of atoms on this plane is 3/2 plus 3/6. 3/6 means 1/2. When we'll add this, it will be 4/2, which will be 2. So after doing this little maths, we understood that on this 111 plane for FCC crystal, total effectively 2 atoms will be there on this 111 plane. Okay, it's touching these 6 atoms, but effectively there will be 2 atoms per 111 plane. I hope this got clear, because we just try to understand till here that how many atoms are there. Now we need to calculate. For linear density, we used to calculate the length of that distance vector. Here it's planar density, so we need to find out the area of that plane 111. Now how to find out the area of this plane? So our plane is something like this, right? All the edges are equal, root 2a, root 2a, root 2a. That is also clear, root 2a, root 2a, root 2a. We need to find out this triangle ABC. We need to find out area of this triangle ABC. Now we know area of triangle is half times the base times the height. Let's say BC is our base. We can take any of the edge as our base. For here we are taking BC. Now the height will be this perpendicular to the base. This is what we call height. But how to find out this? This AO, let's call it AO, or AX, let's call it AX. Okay, X is not good. Yeah, let me call it what? Z maybe. Okay, AZ I need to find out, because BC is how much? Root 2a. BC is root 2a. Now I need to find out this AZ. So you can see this is forming a triangle. You can see this is forming a right angle triangle, this side and this side as well. Okay, so this right angle triangle. If this whole length BC is root 2a, then this length BZ will be half of it, root 2a by 2. That means a by root 2. Now we have a right angle triangle. That means we can use a Pythagoras theorem for right angle triangle, which is the hypotenuse, square of hypotenuse is equal to square of these two sides. That means AB square is equal to BZ square plus AZ square. Now AB square we know, which is root 2 whole square. BZ square we know, a by root 2. So square of it plus AZ square, that we need to find out. AZ length we need to find out. So I'll take it to this side, and this will be, let me first make the squares. That will be 2a square, a by a square by 2. This will be a square, this will be 2 plus AZ square. Okay. Now I'll take it to another side, then it will be 2a square minus a square by 2 is equal to AZ square. Okay, so this will be 4a square minus a square means 3a square by 2 is equal to AZ square. That means AZ distance will be root 3 by root 2 times a. So AZ is root 3 by 2 times a. Now I can do this, root 2 cancelled. On numerator I will have root 3, and a multiplied by a is a square divided by 2. Root 3a square by 2 is the area of the 111 plane. So we found out the total number of atoms on the plane. We found out the area of this plane. Now all we need to do is put in the formula for planar density. Number of atoms 2, total area root 3a square by 2, root 3a square by 2, and we have to give answer in terms of radius again. Now again recalling for FCC, not BCC, for FCC the relation is root 2a is equal to 4r. For FCC, root 2a is equal to 4r. So a is equal to 4r by root 2. Okay, and we have to substitute a square, means a square will be 16r square by 2, which will be 8r square. So a square is 8r square. When I substitute it here, root 3 by 2, a square is 8r square, 4. Okay, so 2 divided by 4, root 3r square. This will also cancel. It will be 1 over 2 root 3r square. Okay, that means the planar density is 1 over 2 root 3r square. 1 over 2 root 3r square. I hope it got very clear, because I took a lot of time so that we can get this thing cleared here. The procedure is same as we did for linear density. First we make our cubic crystal to understand how it is. Then we identify, like we will identify the direction vector. Here we identify the plane. So just by now please practice and keep it clear which plane we are talking about, and then try to visualize or draw that where the atoms, which all atoms are sitting on that plane. Then try to understand how much each atom is contributing on this plane. Like here the face atoms were contributing half, but the corner atoms were only contributing the 1/6. If you can understand directly, very good. If not, then always know that there is some logic there. Try to use that and find out the total effective atoms on that plane, and then use Pythagorean, find out the area, and then number of atom per unit area of that 1 plane will give us the planar density. Okay, so these were the steps for this. Next question, calculate the values of planar density of 100 plane for FCC. Okay, so we have FCC atom. Okay, x-axis, y-axis, z-axis. FCC means all corners are covered, all faces are covered. But here which plane we are talking about? The plane is 100 plane, means it will intersect x-axis at 1 and it will not intersect y-axis and z-axis. So this is our 100 plane. Okay. Now, how many atoms will be on this plane? See, there will be 4 at the corners, and then 1 will be in the center. Now, as I told you, they are touching each other, but here, just to make it look visible, I am drawing they are smaller in size, otherwise they are touching each other. Okay, so just to tell, this is our 100 plane, and we have atoms on the corners, in the face, on these 4 corners and in the face. Okay, so how many effectively are there? You can see we have 4 corner atoms on this 100 plane, and each atom is contributing only 1/4, right? Each atom is contributing, corner atoms are only contributing 1/4. And then there is one face atom which is completely there on this face. Face atom we have 1 and it's contributing completely. And this area of 100 plane is A times A, that is A square. So total contribution will be 4 times 1 by 4 from corner atoms plus this 1 which is completely lying on this plane. So it will be 2. So planar density will be 2 divided by A square. Okay, now the relation between for we are talking about FCC, right? Yeah, so relation for FCC we know root 2A is equal to 4R. So A will be 4R by root 2, means A square will be 16R square divided by 2, that means 8R square. When we substitute it here, we'll get 2 by 8R square, that means 1 by 4R square. 1 by 4R square is our answer. Okay, but we have been given the value of radius, which is 0.143 nanometer. 0.143 nanometer means 0.143 times 10 to the power minus 9 meter. Okay, sorry. Yeah. So yes. So when I substitute planar density 1 over 4R square means meter square, because this radius and this is area, right? When we substitute the value, it will be 4 times 0.143 times 10 to the power minus 9 whole square meter square. When we evaluate this thing, where is my calculator? 0.143 times 0.143 times 4, this will be 1 over 0.0818, and this will be 10 to the power minus 18 meter square. Yes, so when I do this division, I'll get 1 divided by 0.0818. That will be 12.225 10 to the power. When this term will come in the numerator, it will be 10 to the power 18. This will be 10 to the power 18 meter square inverse. Now our answer here, okay, we should shift the decimal point after the first digit, right? It's 12.225. So when I shift it here, it will be 1.2225 10 to the power 19 meter square inverse. So correct answer here is answer A, 1.22 10 to the power 19 meter square. A is the correct answer. Our next question. A crystal plane intercepts crystal axes. Okay. So these are our axes, X, Y, Z, and there is a crystal plane which is intersecting x-axis intersecting x-axis at 0.5 a intercept, y-axis at b, z-axis, oh, it's parallel to the c-axis, means z-axis, c-axis. It is parallel means it will never cut. That means infinity will be the intercept, right? Now first thing we do is we have to find out Miller index of this plane. This plane is cutting x, y, z axis at 0.5 a, b and infinity. First we drop this ABC and we will get the magnitude. Just to write it in not in decimal, when we write it in number, or I want to say when we write it in fraction, 0.5 means half. This is 1, this is infinity. This was just additional step to understand what the 0.5 is. This is just half a, okay. Then we want to take Miller index, so first we need to take reciprocal. When we take reciprocal, this becomes 2, this will remain 1, and 1 over infinity means 0. And since they are not fraction, they are already integer, so we don't need to multiply or divide anything. So our Miller index for plane will be 210. Okay. So Miller index for our plane will be 210. So B is the correct answer. Next, which of the following structure have the highest packing factor? For FCC, if you remember this, I told last time we had discussed that for FCC, the packing fraction is the highest among cubic crystal, and it is 74%. For simple cubic crystal, it is we had discussed, right? Simple cubic crystal, it is 52%. For BCC, it is 68%. And for diamond structure, although we had not discussed, but it's little different from all the FCC, BCC and simple cubic we discussed. So like we have a cubic crystal where in the diamond we have atoms, carbon atoms at the 8 corners. You can see these 4 at the top, 4 at the bottom. But instead we also have these at the half distance, okay? And then the position is here also. So if we study later how we define the basis and how we tell the coordinate, but basically this is how it looks. It's not FCC, it's not BCC, it's not simple cubic. The atomic arrangement is something like this. And the packing fraction for diamond is actually only 34%. Okay, so the highest is actually FCC. Yeah, so these were the 10 questions I had for today's session. Now I think we have some time also, and because these questions were related to the topic we covered till now, so now we can move on to another topic that was started this week at the end, which was about crystal symmetry. Okay, so what do we understand by symmetry? We talked about pattern in the beginning of the interactive session 1 or 2, I think, that we see a lot of patterns, and then we talked about how when we repeat the lattice point we get whole arrangement of lattice point, or when we arrange that repeat unit cell we get whole crystal. But that is in physics, or that is in chemistry, or that is in science. But around us, whenever we see beauty when there is some pattern, or otherwise also, but we see these symmetries in nature around us. Like here, you can see there is some repetition. Maybe you can identify that this is one unit which is getting repeated. From here, it's moved to this distance. From here, it's moved to this distance. So by repeating it after a particular distance is giving this repetition, right? Here, with this flower, you see the petals are repeating after not some distance, after some angle. Like after some angle, it's repeated. Then from there, after some angle, it's repeated. So it's like repetition is happening. Here it was in a linear direction. Here the repetition is happening after rotation, after some angular repetition or rotation, you can say. Right? Now here, this is the wings of a butterfly or a moth. Here, if I repeat this wing at some distance, I will not get this. So it's not this, this is called translation actually, because there is some distance covered. So here if I take this portion, half of it, and take it to this distance, I'll get it not, I'll not get this pattern, right? It will be inverted. Similarly, there is no rotation, because if I rotate it also, it will be upside down. So there is no translation here, no rotation here. What we see here is, if I keep a mirror here in the midway, then this whole thing will be laterally inverted. Like we see ourselves laterally inverted in the mirror. The same way, if I keep a mirror in the middle of this, I'll see this complete thing. So here it's reflection. That means what I want to say is, around us, whenever we see some pattern repeating, it may be translating, it may be rotating at some particular angle with respect to each other, or it may be reflection. If we imagine a plane, then it's reflection of the other half, like this. This is what are the different types of way we obtain a symmetry. Okay. So yeah, like here it was translation, translational symmetry, rotational symmetry, reflection symmetry. These are different symmetries we see around us. Now when we talk about crystal in specific, then we have these 4 types of symmetries or symmetric operations. Translation symmetry, I think you already understood. If we have a unit cell like this, and I repeat it after every distance, then I'll get translational symmetry. All will look same, right? Now, what is rotation symmetry here? If you see, take one in 2D, I'm talking about right now. Let's say corner atoms are there. If I rotate it by 90 degree, I take this here, take this here. Let's say it was A, B, C, D. So after I rotate it by 90 degree in this direction clockwise, then it will change to A will come here, B will come here, C will come here, D will come here. But we will not be able to distinguish these two. Why? Because the atoms' positions are all same. So even after 90 degree rotation, it looks exactly same. That means the symmetry is maintained. Nothing has changed. This is what we mean by rotational operation. That even after doing that operation, that symmetry operation, if the unit cell or that crystal looks still the same, then we call that symmetric operation. This is for 2D. For 3D, we can understand we have a 3D unit cell. Here also, if you consider, this is my rotational axis, and you rotate it from here to here, this atom will go here, this atom will come here, and it will exactly look same, right? So this is what we mean by rotational symmetry. And this can be done in different direction. You can consider rotational axis here and rotate it like this. You can consider rotational axis here and rotate it like this, or you can consider it outwards the screen and then rotate it like this. So we have different some 4-fold axis, 2-fold axis that may be discussed in detail later if it's required. But I'm just introducing you guys to this translate symmetric operations. So just try to understand what it means and how we get things. So this was rotation. Now reflection. Reflection will be, if I take, this is again in 2D, if I go, this is my plane or unit cell in 2D. It has atoms. Even if it has atom at center, or the edges, say some kind of unit cell it is, which has like this. Now if I consider a plane passing through center of these atoms, then I'll get this complete picture. Yeah, because all these will give me this reflection and the remaining half will also be completed. So this particular plane will give me the plane symmetry. Also, when I'll keep my plane here, I'll be able to get the complete picture. Also, when I'll keep it here along the edge diagonal, still I'll get. So we have 3 different kind of reflection symmetries here. And this is what we mean by reflection symmetry. Then inversion symmetry. In 2D, it's like saying I have a unit cell like this, and if I consider this point as inversion point, then I have to take everything to the opposite. This I have to move, like it is at some distance a, then I have to make it minus a. This is at some distance b, I have to take it to minus b, and they will be exactly same. This will go here, this will come here, this will go there, this will come here. And again, this will look exactly same. Like initially say A, B, C, D atom. After I apply this inversion symmetry, this will be C, this will be A, this will be D, this will be B atom, right? And I won't be able to distinguish between these two because right now I am naming them for just to understand, but otherwise the atoms they will look exactly same. So that means even after doing this inversion, I'll get the exactly same unit cell. So that means this inversion symmetry is also an operation. In 3D also similarly, maybe it's a little difficult to visualize, but here at the body center we'll have inversion where this corner atom will at the back will come down at the front, this up at the front will go down at the back, this up and back will come here, and this will come here. So all will be inverted if the inversion symmetry is at the body center. So these are the different type of symmetry operations using which using these symmetric operations we can have all types of crystals. We can make all types of crystals that are there in nature. That means they are grown out based on these symmetric operations only. And then based on this, we have, based on this rotation, reflection, inversion symmetry, we have something called as point group. If it would be required, we can study it in detail. Otherwise, just telling you for information, we have something called point group. There are 32 types of point group for 3D, and if we include the translation operation also, then we have something called space group for 3D. Again, I'm telling you, and there are 230 types of space groups for 3D. So this is just for understanding that we have something known as symmetric operation that we find in nature, and then we brought it to crystallography and to understand how crystals have different kind of symmetries in them: translation symmetry, rotation symmetry, reflection symmetry, inversion symmetry, and then using these symmetries, how we get these symmetries, we get all types of crystals that we see around us. Again, why we want to understand? Because if we can categorize based on that this kind of crystal have only this symmetry, maybe we can understand their properties, that these kind of crystals have this kind of properties. But here, just for introduction, that something like symmetric operation exists, and this is how we uh, understand them for our unit crystals. Okay, so I think this much is okay for this session, and if you guys have any doubt, you can ask, or other finish today's session. Next time we'll meet, then we'll be discussing about X-ray. So X-ray diffraction is very important, very useful technique whenever we go in experimental physics or experimental chemistry. We use X-ray diffraction phenomenon. We'll understand its theory also, but we use it to identify the element that we are making or that we found or anything, but it tells us about which kind of element is there that we are checking. So it's very powerful, very useful technique. So we'll understand that. Before that, we understood all about crystals, atom position, planes, because plane is very important when we are talking about X-ray, X-ray related thing, X-ray diffraction related thing. So I hope the everything about direction, planes, and how to find out linear density, how to find out planar density is clear. We did a lot of problems so that it becomes very clear for us. And if all this is done, and yeah, again, if no question is there, then okay, I'll end today's session. First, stop the recording.